All right, well, welcome to the second class. So just a couple of things before we actually continue with the presentation. I wanted you to pay attention to a detail that is on your syllabus and is actually to do with feedback and communication. So you can give me feedback in any form. You can talk to me, you can email me, you can drop by my office hours, but there's also an anonymous way to give feedback as well. And that is via this form. So if you actually follow the link that is provided on the syllabus, you will be taken to a web page that looks like this. And basically you can just type in anything in here and submit. And I will not know who did it. So this is when you're, for some reason or the other, not comfortable providing your name. Okay? There might be, if you're pleading for homework to be delayed or something, you maybe don't want me to know who you are, this is the way to do it. So again, there could be a situation where you're a little more comfortable not signing yourself. And let me just demonstrate how it looks like on the other end. So I can type in here, hello, and submit. Okay. And then let's see, what do I see on the other end? I need to go to where my drive is. My computer cannot seemingly adjust to the situation of being projected. Google Drive. So these are the forms. Can I get to my Google Drive, please? I'll have to disconnect to find it and then project it. Things get changed when I'm projecting them. Oh, come on. The little usual link to Google Drive has now disappeared from my... Okay. From my view, I'm getting there. Okay, so on my drive, I can find the Google form, and all I will see is a spreadsheet that looks like this. So the spreadsheet looks like that. And you can see some, so here is the entry, there's a timestamp and hello. And then you can also see what people at some point last year, this was probably a review, so when there's a review for exam coming up, I ask people to submit questions that I will review in class. Okay. So that just gives a review aid. So again, if this is a more comfortable way to communicate, go ahead and use it. So that is the point number one. Second point number one is that I mentioned last time that you should be making it to seminars. So the first graduate seminar is this Monday, 3 to 4, and actually 2 students will be presenting. They're representing, they're winners of the regional contest in the Society of Petroleum Engineering, and they're going for international competition in Dubai during the annual technical conference and exhibition by SPE. So it's one of the largest SPE conferences. So if you want to see how you should be looking like presenting by the end of your finished studies, those are some of the top presenters in the department. So I think it's also a way to see what 2 people in this department are doing for research, and B, to see how you should actually aim for presenting down the line. That said, come and be critical, ask questions so they can actually improve upon their presentation. All right, so that is what I had to say for the small stuff, and let's now go back to our presentation from last year, last time. So I'm still busy motivating why do we actually need to study transport phenomena. And one motivation that we had is that oil and gas is at the foundation of society. We need oil and gas to function, and it is job of petroleum engineers to actually deliver that oil and gas to society. So essentially, we need to be flowing 3 different types of fluids around, and we basically quantify last time how much we actually need to do a day. So basically, around 80 million barrels is equivalent to filling up an Olympic pool 2.5 times every minute during an entire day. So that is the amount of oil that is flowing around. Now, we flow and transport oil and gas in all kinds of big pipes, and I'm going to now, sort of in a cartoonish way, present all kinds of size of pipes that we actually encounter. And what I want you to visualize is that you actually have to be able to span very large scales. Okay? So scales of flows go over numbers of orders of magnitude. So you could have large piping like this. That's part of industry. It's also actually hidden in this tanker of that size. So basically, you need to, first order of knowledge you need to have is what is the flow in a pipe. So if you just take a piece of paper, let's just remind ourselves, oh wow, hi. So if you actually have a pipe like this, and you have a Newtonian liquid, and you have a steady state flow, and the tube is horizontal, it has given the dimensions of 250 millimeters in length and diameter 5, and I have a pressure gradient that is driving the flow, and it's given as 1 kilopascals per meter. How much force in the direction of flow does the liquid exert on the tube? Can you think about it on a piece of paper? And the second question, just to actually compare, often we actually need to do most of the questions are actually comparing different situations of what is better than the other. Now, if you actually have a similar pipe just bent, okay, and I have the same pressure gradient, the same length, the same diameter, and I'm wondering about the force in the x direction, which was the same direction as previously, exerted by the liquid on the tube. Is that force greater or smaller than the previous question force? So I'm essentially wondering about Fx in both this situation, x being this direction, and this situation, and I'm wondering what are the differences. So I'm not going to answer the question. I'm just going to leave you wondering, because that does good things to you. So you can keep thinking about it. So let's see all of these pipes that might be bending and might not be bending. One of the largest ones is Trans-Alaska Pipeline. It is more than 1,000 kilometers long, and it was built in 1977. And you can also see the network of the natural gas pipelines in United States. This is again taken from that Energy Information Administration website, which is a good source for all kinds of stuff. So you can actually see a network of pipes. So we are actually often dealing not just with one of the fundamental questions will be what is happening in a pipe in terms of all kinds of transport, okay? But also beyond one pipe, I actually have to often talk about the network of pipes and what is actually happening when multiple pipes are combined. And even if I actually go down to a very small scale, any standard rock you could walk by, if you go to Barton Springs, Greenbelt or something like that, if you take a core and actually get some X-ray vision, which we have quite a bit of X-ray vision here in the department, in the basement, both Dr. DiCarlo and Dr. Espinoza have X-ray machines in their labs. So in Dr. Espinoza's lab, you can actually take things on this micro scale. So this is 1.25 millimeters across, blown up. And the scale is essentially, the resolution is essentially equivalent to your hair or diameter of your hair. And this is inside a sandstone. You can see individual grains. You can see that they're bound together in a sandstone. And you can see pore space in between. So where are the pipes? Well, I could actually imagine that as I'm flowing through this sandstone, I actually have a series of pipes of varying diameter, but nevertheless they're there. Now, can I percolate from one side to the other? This is just one slice. Can I go through the pore space from one side to the other? Oh, I'm stuck. No matter what I go here, I'm actually stuck. Here I'm stuck immediately. Here I'm stuck immediately. So no. So this is a 20% porous Berea sandstone. How do I flow through it? Third dimension. So in third dimension, these spaces actually connect. Okay? So beware of two-dimensional modeling. In reality, so you have to always double check your assumption. Your simplest model will always be two-dimensional. Ask yourself, well, what does this do to actual three dimensions? Because at 20% porosity, you will by and large never percolate from one side to the other. Okay. To percolate in two dimensions, you need about 55% or so. Okay. And if you ever work on the micro models, that's going to be a challenge, because micro models are these models that kind of are quasi two-dimensional, because you have like small pillars in your space. So in order to percolate, they have to be 55% porous or more, and rare rocks are of that porosity. So how do you relate that to whatever it is that you're analyzing there? Okay? And then of course, we have all of this small stuff inside the rock that is connecting to either fractures or whatever damaged part of the formation next, and then next to a wellbore. So we have this communication across pipes of various scales. So if you look at how the fluids compete in this pore space, we will mostly work through single-phase flow in this course, but nevertheless, this industry is founded on multi-phase flow. So if you actually have multiple phase fluids, so this is, for instance, air, water, inside glass beads, you can see actually interfaces curving in throats, such as here. Okay? And then you could even have like three. So here, this is oil, this is water, and this is air that actually accidentally got into this experiment. So this is air, this is water, and this is oil. So this is actually, these images were actually part of my PhD thesis. Now, if you think that micro scale is small, most recently we have a lot of research work in shale. Shales, by definition, will have grains that are micron scale, if lucky, and then spaces in between those grains are submicron scale. And if we go to actual, so these would be the grains here. But then you also have organic material that is wedged in inside the pore spaces as well. So you actually have original porosity that is on submicron scale, and then you have organic matter within that porosity that is reducing those sizes, pore sizes, even further. And that's essentially where the gas is typically stored. So you actually have, you're flowing through nanometers. So this is 2 microns altogether. You're flowing through nanometer scale porosity. In nanometer scale, we have a different scale. We actually have mass transport that is competitive with momentum transport. So suddenly all of the equations that we have over the time developed intuition with do not necessarily apply in the same form. Okay? So you have to be aware of that, and that's this pushing the envelope in research as usual. What is going to be a thing to study 10 years from now, 15 years from now, we don't know. That is the nature of research. But nevertheless, you need to know the fundamentals, and fundamentals we're covering in this course. So we will observe, and then we will observe 3 major scales of the phenomena in this course. One of them is macroscopic, which is also referred to as continuum scale. That's the scale where I don't see individual molecules and everything is continuous. So I can think about my viscosity or my pressure or velocity. All of those fields are actually continuous fields, okay? Mathematically continuous fields. Then I have microscopic. This is actually from the cover of your textbook. Let's see, right here. So then you have microscopic, that is basically micron to centimeter scale, and then the molecular or subatomic scale. We know that everything ultimately happens on this scale. We just don't have the luxury of analyzing everything on this scale. And our practical, our industrial interest is on macroscopic scale. So this bridging intermediate scale is basically the key thing in science and engineering. And how you bridge the scale is not necessarily easy. I will also warn at this point that whenever you hear micro, macro, meso, those terms are specific for discipline. Okay. So you have to actually always ask the person, what precise scale did you mean by microscopic? What I traditionally have called microscopic was always in this micron to centimeter scale. But if you actually talk to chemists, which with this emergence of shale and nanometer scale pores, their classification of pores is entirely different from what we would call, so they're called macropores that are size 50 nanometers. Okay? Their macro is 50 nanometers. So you have to be careful. Micro, macro, meso are always relative terms to whatever people are used to calling micro, meso, macro. So just be careful when communicating across disciplines. All right. So our key assumption in this course is the continuum of space and time. Even though we know that the matter is composed of molecules, and it's these molecules and their movements around that they're agents of transport for all 3 heat, momentum, and mass. So in many applications, or in most applications, the number of molecules is large enough to actually speak of a phase or this continuum matter that has certain physical properties, and it is those physical properties, such as temperature, pressure, and so forth, that we actually measure on larger scale. And we can successfully also solve many problems using those assumptions. So basically, we are interested, from the engineering standpoint, to solve them on larger scale. We are interested in what's going on in the reservoir on a larger scale. Now, how do we build up across scales? We have 3 avenues: theory, experiment, and computation. Those are the 3 legs of. In each, whatever it is that you choose to do in your research, and you're probably better equipped or skilled to do one or the other, but you have to do a little bit of everything, is that you have to make sure that you're having a scientific method. What does it mean to have a scientific method? how do we build science little by little? What is the starting point? Hypothesis, correct. So I will assume that something is correct or not correct or whatever it is that the situation might be. And then what? Prove or disprove. So this is the key. I actually have to be able to prove or disprove. So I have to be wise in formulating my hypothesis so that I can prove it or disprove it with the tools I have. And that is going to be a key assignment for you in research. When you go, so first you pass, if you're a PhD program, you pass the qualifying exam, which is more or less just theoretical knowledge. Okay, did you actually just absorb information given in courses? But after that, you actually have to prove to your committee that you know how to formulate hypotheses, that you have read, and for that you need to read literature and need to know where is this little piece of knowledge that needs to be found that you can contribute to. So it's matching what needs to be done with your abilities and your preparation. And then you have to present your committee with the plan. Okay, I'm going to do this, and if I do this way, I'm going to learn this. Three or four objectives that you're going to pursue. Okay? And committee will say, well, this is reasonable, and you will typically have to show a preliminary result or two that you're kind of on the way of getting there so that it looks feasible. Okay? And your committee will assess, well, given this person in front of us, we think he can complete this, he or she. Okay? And that's not always, because you can always want there's a whole lot of things that can be discovered, but you also have to do it within 5 years. Or by the time you're in front of a committee, within 4 years. Okay? So basically, the committee has to judge, okay, this is doable in a reasonable time frame. So you have to be able to bite off precisely the chunk that you can actually deliver. Okay? And then your thesis is the contribution, so little by little we build the knowledge overall. So you have to be, at the same time, you have to find something that is needed, but you also have to be practical. And I'm going to quote a friend of mine who says, it actually makes sense. You can always say, and aspire, say, what if it takes me 10 years to finish whatever it is that I set out to finish, right? Well, no. If you go and work, you will be trusted with, for instance, $1 billion to develop a project for a company that you work for. And they should have reasonable trust that you can actually deliver whatever is promised to deliver within certain time frame. So there is the practical component. As much as we could aspire to contribute to science, we also have to be a little bit practical about it, because projects have to move on in stages. So you have to be able to gauge how much you can do, and that you do by reading the literature and informing yourself about it. So you got a lecture now on how to actually go about your project, but that is important in graduate school. And I'm actually just going to play, I love this video by Richard Feynman. Does everybody know who he is?
How we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences.
Is it playing?
See what, if this is right, if this law that we guessed is right, we see what it would imply.
Right, but there should be,
and then we compare the results to nature.
Oh, this is annoying. This system should actually, once I'm actually connected with HDMI, it should project sound to speakers.
Or we say compare to experiment or experience. Compare it directly with observation to see if it works.
And apparently I cannot. It just...
If it disagrees with experiment, it's wrong.
Okay, let's...
It's the key to science.
Oh, hi. All right. You have just been exposed to what I was listening to last night. That's John Legend, by the way. All right. Let's try now. Technology.
It's therefore not unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about.
All right, I'm going to start.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process.
So now
First, we
lost
guess
the
it.
sound.
Then we...
This HDMI is not transferring sound.
That's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience, compare it directly with observation to see if it works.
Okay.
If it disagrees with experiment, it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are, who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Well, I'm going to invite you to...
It's therefore not unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then how can you say it's likely, that it's unlikely? Well, that's the way, that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I see around me, I think that it is much more likely that the reports of flying saucers are the result of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence. It's just more likely, that's all. And it's a good guess. And we always try to guess the most likely explanation, keeping in the back of the mind the fact that if it doesn't work, then we must discuss the other possibilities. There was, for instance, for a while, a phenomenon called superconductivity. There still is the phenomenon, which is that metals conduct electricity without resistance at low temperatures, and it was not at first obvious that this was a consequence of the known laws with these particles, but it turns out that it has been thought through carefully enough, and it's seen, in fact, to be a consequence of known laws. There are other phenomena, such as extrasensory perception, which cannot be explained by this known knowledge of physics here, and it is interesting, however, that phenomenon has not been well established, and that we cannot guarantee that it's there. So if it could be demonstrated, of course that would prove that the physics is incomplete, and therefore it's extremely interesting to physicists, whether it's right or wrong, and many, many experiments exist which show it doesn't work. The same goes...
Okay, so I'm going to stop it here and invite you to watch it on your own time, since I don't even know that the last row can hear anything. Could you hear anything? Sort of. Well, so somehow it actually, this projected without whatever happened here, I don't know. The technology is not, so normally if there is HDMI here, then entire experience of my computer should go to the system. But question is, are there actually speakers in this room? And that I don't know. So maybe I'm projecting to imaginary speakers. All right. So basically, again, back to scientific method, you have to look at the problem and try to answer the question. And you're not always, as Dr. Feynman pointed out, going for possible and possible. You're really comparing things, what is likely, what is more likely. So it is always actually good to have scenarios to compare, because that often is a vehicle for you to actually figure out something new. And so you compare to something that is known and well studied. And this is where reading the literature comes in handy. So basically, we will, and we do in this class, we postulate conservation of mass, momentum, and energy, and we essentially build from the theory from there. And the key tool for solving problems are actually conservation equations. We will not do any experiments. You might do experimental work in your research. Experiments are a very important part of verifying any theories. Don't anybody ever let you make you think that you will be just able to push the button on your software and solve all of the problems of this world. That's not how it works. Simulation, experiments, theory, they all work hand in hand, and they often work on different scales. So with simulation, you will often go into the details of that core that you encase in your lab, and you can't look inside unless you really tear it apart. Okay? It's the simulation that allows you to, given certain information, that you can actually simulate what's happening inside. So that's what I mean by going hand in hand. Often simulation actually allows you, and the simulation does come from theory and solving equations, so equations can actually, if you have a closed solution, you can actually just plot it and know what it is. That gives you the detail that you might not have in the lab. In the lab, you often have endpoints. You have endpoint pressures, mass in, mass out, you weigh things before and after, that sort of thing. So you typically just know sort of like endpoint boundary conditions, and all of the other details you resolve by either theory and simulation. So all of them work together. So conservation equations are basically tools and the language of transport phenomena. You can just see that by opening the book. I have a comment on that. So my first 2 years of teaching here, I was preparing class often on the bus. I had a 30-minute bus ride to campus, and I would open Transport Phenomena book. And the moment I did, and the moment people saw these equations in the Transport Phenomena book, I would hear everybody's and anybody's problems with math during their school. So watch out if you open the book on the bus. Everybody will feel like they need to tell you all of the problems they had with math. And interestingly enough, when I taught reservoir geomechanics, that was most text and figures, nobody said anything. But the moment they said, and I'm like, I'm preparing for class, I gotta get into the classroom in half an hour. So anyway, so watch out if you open the book during the talk. And if I'm a Richard Feynman fan. If you actually follow this movie, you will see his comments on math and physics. So math is going to be the tool to solve the physical problems. And yes, it can be frustrating sometimes, and it can take 3 or 4 pages to solve, but nevertheless, it's a key tool that we will have. Now, if you look at the syllabus or what we are actually going through, there is actually a similarity in our chapters. So when we look at the momentum transport, we will start with the molecular basis for viscosity, and then shell balances, which is going to be our tool to solve equations, then equations of change, and then following some other problems. And then we will turn our attention to porous media. And energy and heat transport will again follow the same molecular basis, shell balances, equations of change, and then mass transport the same. This is also the reason why we are studying all 3 together. Mathematically, they actually get curiously similar, even though we're modeling completely different phenomena, and even though the boundary conditions we apply will actually, often sometimes they will give similar solutions, but sometimes actually completely different. So in that sense, we will have enough complexity regardless of the equations that we're solving and the procedures we're applying looking somewhat similar. Okay, so if we now go back to the key observations we made last time, the motion or flux occurs whenever there is a gradient of potential. Whenever I disturb the systems, in other words, I'm going to have some movement to actually make it back to equilibrium, and that's the transport process. So I can move different things, but this disturbance will actually cause transport. It's typical in whatever we do that particles move in attempt to diminish this gradient that I created by disturbing the system. So this is this molecular basis. For all of the phenomena that we look into, we actually have a molecular basis, even though we apply continuum equations. So the simplest, in order to apply continuum equations, I have to have a functional relationship that relates my flux of particles, some sort of continuum flux of the matter, and that gradient. Okay. So what is the simplest functional relationship that humans can come up with? Constant things. That's not going to move anything anyway. We're not going to resolve this thing. We're not going to get to equilibrium. Beyond constant, linear. So yes, it's true that simplest one is the constant, but that's not going to solve our problem. Linear is one of the simpler relationships. So what are some examples? Electric current. Okay. What are some other examples? In porous media, what is the most important law? Darcy's law. What does Darcy's law say?
The flow is proportional to the heavy.
Proportional meaning implying linear relationship to gradient of pressure. So gradient of pressure is my driving gradient. Okay? And I have coefficients of proportionality. What is the coefficients? What are the coefficients of proportionality? Permeability and viscosity. So I'm separating the two, but they're together this one coefficient that relates the flux to the gradient of pressure. Most of the laws actually have that form. Any other laws? Hooke's law. Newton's law. Okay. So most of the law, the moment you say law, most likely that relationship is actually linear. Even when we know that it's nonlinear, and often it is, back to simulation, it's extremely hard to implement in most situations. It's extremely hard to add nonlinearity because suddenly your computational time will go through the roof. So first approximation is typically linear, and we often go with it and say, okay, this is going to be good enough, unless something tells me that I will not be able to compare two situations. This is go back to the comparison that Feynman mentioned. Okay? We often learn by comparing different scenarios. And if this first order approximation is enough for me to compare two situations and bring a sound decision that will actually have key components of how flow, for instance, happens, where are my flows going, and so forth, and in which time frame. If I'm going to get a good gauge from that linear law is good enough. No need to go any more complicated. So I go more complicated when I know I have something complex, and that typically goes for fluids that don't behave in a linear way. So I might have a foam, or I might have a drilling fluid that is laden with a lot of solid particles. Those types of fluids are not simple enough, and they will typically behave in a majorly nonlinear way, so that using linear laws on them will not, or have the relationships have to be improved for me to make sound decisions in comparison to different situations. So don't go more complicated than you need to. Okay? So, and one of the key thing is that having an engineering judgment is to simplify as much as you can, but not more than you need to. Okay? So you can start reading the book. I will not go over the initial chapter 0 in there. I will rely on you reading that yourself. And if you want to actually have a little bit, some of you might be new to petroleum engineering. It's actually very natural for petroleum engineering to have all kinds of other types of engineers within. There's a very colorful and simple book called Oil and Natural Gas by Society of Petroleum Engineers. It's an easy read. And if you need any other additional information, this is a whole lot of statistics that is available on Energy Information Administration website. Also, we will actually have homework that is one portion of it based on Matlab. I don't necessarily endorse Matlab in its own. You could use any other tool in terms of a computational environment, but Matlab is simple enough for whatever we need to do in class. It's also free to you as a UT student. So you can actually just go and check on Students tab of this website, and all you need is a UTexas email address to register, and you can install it on your computer. It's also available on most of the computers on this campus. If you're into open source, alternative is Octave. It does work. In all of the fundamental stuff, it works pretty much the same as Matlab. Where you will see these differences is specialized toolboxes. Okay? So it's good enough to actually do a quick assessment. For any kind of more involved simulation, you would typically go into a compiled language like C, Fortran, and so forth. Okay? So that you might need to do for your research. In quite a number of courses, professors will kind of expect that you're operating. It doesn't have to be Matlab, but it's something that you can quickly plot the results, and please plot in Matlab. Excel is horrible. So Excel is good for data analysis, but not for plotting things. So in any event, now would be a great time to actually, if you don't know Matlab, to go and familiarize yourself, so it just becomes a tool for you to deal with homework quicker. Okay? And you can, on this link, and I posted this already in this lecture, you can follow this link. There's an overview by Dr. Balhoff, who used to teach the class that I actually now teach for undergraduates, that actually has Matlab fundamentals as part of it. So there's like a number of videos you can just watch, and if you open Matlab while watching them, you'll be good to go. So do yourself a favor and just get it done now that you don't have a lot of homework. All right, so this is our introduction, and I have 5 minutes left, so I am going to start with the viscosity, or our first topic. And before I start with the topic, I'm going to comment on something that I think it's worth to comment. We live in a digital age. So I will approximately have half of the material in PowerPoints, the other half will be written. But there is actually research now, serious research, that says that if you do take notes, handwritten notes, you're better off in retaining the material than if you're typing them in. So there's some connection between mind and the hand that is there, that is innate to us. And also when writing, we're often not necessarily as quick. So it appears that when we're writing down the information, we're also processing it at the same time, and we're typically writing a processed bit of information, a summary, as opposed to writing down verbatim, because most of us are not as quick. Whereas when you're typing, you're more likely to just type in verbatim the sentence you heard, and because you didn't process it, you don't retain it as well. If you're interested, I can actually point you to the research, but I think it's something worth pointing out, that there is actually something to be said about the traditional writing. Now, the tablets, again, you decide what you're most comfortable with and what you're efficient with. This is just a piece of information I wanted to share. It is good to have notes that are electronic, are searchable. You can place them in one spot. You will not lose paper while moving necessarily. You can lose paper by losing your disk, but you will not. There's a way to do that. So again, try to do it. There's also these days, there are tablets that can actually allow you to write into a notebook. That again applies the same rule applied. That you will process information, and because of that summarizing, you will actually be able to better retain the material. So again, I will show quite a bit of PowerPoints, which are actually, it looks like bad. I should be writing, but there is also a power of pictures that I can use in PowerPoint that I cannot do with my handwriting. But if you are actually writing down the notes, you will be better off if you're writing them down and by paper. And again, don't worry about not taking everything down. I post all the notes. I will post this when I get back, and you do have the videos, so you should be good to go in terms of being afraid that you cannot catch something. All right. So let's start our microscopic momentum transport. Okay? So we can check off introduction, and now we will start this large topic called microscopic momentum transport. And first topic that we will be involved with will be viscosity. Today we will define it, and then we will go into molecular basis and explanation for viscosity that we observe. So viscosity is one of these macroscopic properties that we measure on our engineering scale of interest, but its origin is molecular, and we will look into that. And then we will put that aside and say, good, now we know what's behind our continuum assumptions, and then we will actually start solving problem on this continuum scale. And the tool that we will have for steady state problems is called shell balances. But of course, a lot of problems have time components, so we will then after that deal with equations of change that actually have time derivative in there. And we will actually then go back to some specific solving methods for complex cases that are called stream functions and velocity potential. And in my personal opinion, this is probably the most complex part of the entire course. And those of you who have taken the course already and are sitting here for review can confirm that or not. Am I correct? Or is there anything else that is more difficult? I don't think so. So be prepared for this to be, if you're struggling with it, don't worry, everybody does. Okay? And my joke in this course is that you have to teach this course 3 times to actually for things to flow out immediately. Right? And then we will actually turn our attention to non-Newtonian flow, even though most of the theory, most of the simple situations and solutions are for Newtonian fluids. Most of the ones of engineering interest in petroleum engineering are either non-Newtonian, or even if they're Newtonian, they're extremely complex and heavy and high viscosity and so forth. So they're difficult fluids to deal with, and we will touch upon that in non-Newtonian fluid flow, and then the rest of the course. So the objective for the microscopic momentum transport is to define viscosity and Newtonian fluids and what sets them apart, and explain the molecular origin for it. And we will also estimate viscosity of complex fluids such as suspensions. And we will also define this momentum flux tensor and its components in different coordinate systems and in 3 dimensions, which is what makes actually this part complicated. And we will differentiate molecular contribution for any kind of external ones and see how do we put equations together that have all of those parts together. Okay? So first, quiz, so take a piece of paper since this hand-brain communication is important. Let's practice it. So I have top plate that is kept still, and I have bottom plate that is moving with velocity Vx. And let's say that I start that motion, I wait a little for flow to stabilize. Approximately, please draw the steady state velocity profile, assuming laminar flow. What did you draw? Water circle?
No, that's right.
The top one is still. Okay. So basically that one doesn't move, the below one is Vx, and I basically linearly change it. That is the fundamental assumption of Newtonian fluids. If fluids behave that way, approximately, we call them Newtonian. And we will apparently go into details of that on Monday. So I see you next time. I will post this PowerPoint